Alright, so this is the section A for January 2012. So a ball of mass 2.0 kilograms initially at rest is acted on by a force F, which varies with time t as shown by the graph. What is the velocity? So we can work out the change in momentum because it's going to be the area, so it'll be half times the base times the height, which is 40 Newton seconds. So if it weighs 2 kilograms, and that's the change in momentum, the change in the speed is going to be 20, which is answer A. So question 2. A body X moving velocity V makes an elastic collision with stationary body Y of equal mass on a smooth horizontal surface. Which line A to D gives the velocities of the two bodies after the collision? Okay, so the total momentum going in is mv. So whatever the momentum is afterwards, it would have to add up to mv. And if it's elastic, you also know the two kinetic energies should add up together to give you half mv squared. So if we look at line number 1, if you add the two momentum, so you'd have mv over 2 minus that one, so it gives you a total momentum of 0. So it would be the same with this one. And in this first one, the total kinetic energy is half mv squared. And then you've got this scenario C isn't possible because y has to move. If we're moving to the right, which v being positive implies, y must be travelling faster than x, so C is impossible. That would leave it being D, where all of the kinetic energy is transferred. Ball of mass m, which is fixed to the end of a light string of length L, is released from rest at x. It swings in a circular path, passing through the lowest point y at speed v. So, if the tension in the string at y is T, which one of the following equations represents a correct application of Newton's laws to the motion of the ball at y? So in terms of the forces at y, if it's a force T, and there'll be a force mg acting against that, so the resultant centripetal force would be T minus mg, which must be equal to mv squared over L at that point. So we're looking at answer number C once we work out the centripetal force. A disk of diameter d turning through a steady angular speed at frequency f about an axis through its centre. Centripetal force on an object O of mass m on the perimeter of the disk. So the radius will be d over 2, and the angular speed will be 2 pi f. So if we square that, it's going to be 4 pi squared f squared, which you need to multiply by r, so then you'd put your d over 2 in. 2 gives you 2 pi squared f squared d. 2 on the centripetal force, so we actually need to multiply it by m, so you'd have an m in there. So we need a 2 pi squared m f squared d, so option number C would be the correct one. What is the angular speed of a car wheel of diameter 0.400 meters when the speed of the car is 108 kilometers per hour? So that would mean the velocity, or tangential velocity, would be 108 times 10 to the 3 over 3,600. So let's type that in, calculate before we go any further. So 108 times 1,000, so it's meters per hour, divided by 3,600 gives you 30 meters per second. And so we need to divide that by 0.2. because that's the radius, gives you an angular speed of 150, which would be option B. Which one of the following statements is true when an object performs SHM about a central point O? So we're looking for the one that's true in this case. So the acceleration is always directed away from O. Rubbish, it's always directed towards O. The acceleration and the velocity are always in opposite directions. No, that's not true either. The acceleration and the displacement from O are always in the same direction. No SHM, they have to be in opposite directions, which leaves us with D. The graph of acceleration against displacement is a straight line. Yes, because it has to be directly proportional, so yes, it would be a straight line graph. A body executes SHM. Which one of the graphs A to D best shows the relationship between the kinetic energy and the distance from the centre of oscillation? So, let's think about this. The further you are from the centre of oscillation, the smaller your velocity is going to get, because it will be maximised at there. So we can already eliminate anything that suggests velocity is not maximum initially. We also know that the acceleration is directly proportional to the displacement, so that would mean, however, the velocity is not going to have a fixed gradient because the acceleration is going to change, so we can forget that one. And we know the acceleration object will be maximum at the furthest point, furthest away, so that would mean the gradient of your velocity graph would be maximum there, so your gradient of the kinetic energy should be the greatest negative number, which gives you A here, this one. The mechanical system is oscillating at resonance with constant amplitude. Which one of the following statements is not correct? So what do we have? The applied force prevents the amplitude becoming too large. I don't know about that, that doesn't seem right, so let's move on and check the others. The frequency of the applied force is the same as the natural frequency, so it's at resonance. So the frequency of the applied force is the same as the natural frequency, that's true at resonance. Total energy of the system is constant, that's true, that's always true. The amplitude of oscillations depends on the amount of damping, that's true. More damping is smaller amplitude, so exactly right, this one is the one that's not correct. Which one of the following statements about Newton's law of gravitation is correct? It explains the origin of gravitational forces, not really, it doesn't explain where they come from, just models it. It explains why a falling slab burns up, no, that's to do with like friction. Why projectiles maintain a uniform horizontal speed, no, not really, it's nothing to do with that. How various factors affect gravitational force, yeah it does, that's exactly what it's about modelling. If an electron and a proton are separated by a distance of 5 times 10 to the minus 11, what is the approximate gravitational force of attraction between them? So we need the two masses, so 1.67 times 10 to the minus 27 times 9.11 times 10 to the minus 31, so that's the two masses times g, so 6.67 times 10 to the minus 11, and divided by the distance squared, which comes out at 4.05 times 10 to the minus 47, which is roughly answer number C. A spherical planet of uniform density has radius r, which line gives expression for the mass of the planet and the gravitational field. So mass would be density times volume, so density times by 4 over 3 pi r cubed. So we're looking for 4 over 3 pi, so that one's got r squared, so that's wrong, so that's got r squared, so that one's wrong. And that's the mass, and we're looking for the field strength, so you'd have the mass on the top line, and you'd have that multiplied by G, and then you'd have R squared on the bottom line, so that's going to cancel that, leaving you 4 over 3 pi RG rho. So that's going to be 4 over 3, which will have R in it, so it's going to give you answer B. Okay, the gravitational potential at the surface of the Earth of radius r is V. What is the potential at height r above the surface? So it's a distance of 2r from the centre of mass. So we've doubled r, which means you would have halved V. So it's going to be this one here. A satellite is in orbit at height h above the surface of a planet of mass m and radius r. What's the velocity? So we're just equating our two equations, so gmm over r plus h squared, so cancel m's, cancel 1 r plus h, so velocity would be gm over r plus h, and then square rooted, which is answer A. Repulsive force F acts between two positive point charges separated by distance r, or with a force between them if each charge is doubled. So that means that the top line has been times by 4 because it's 2 times 2, and the bottom line is going to be a half squared because the distance is halved. That's going to be 4 over a quarter, which gives you 16. So it'd be 16 times the force. Distance between 2 point charges of 8 nanocoulombs and 2 nanocoulombs is 60 millimeters. At a point between the charges, the resultant electric field strength is 0. So how far is this point from the 8 Newton charge? So let's call that one D1 and that one D2. So essentially 8 over k d1 squared is equal to 2 over k d2 squared. We also know that d1 plus d2 is 60. So let's cancel those, cancel that. So we've got square numbers, top and bottom, so we can do 2 over d1 is equal to 1 over d2. So we get that d2, 2 times d2 equals d1. Or we can take that 2 to the other side. So we get that 3 over 2 d1 is 60, so 60 times 2 divided by 3. So we get that d1 is 40 millimeters if we solve essentially these two equations simultaneously there, which is answer number C. Which one of the following cannot be used as a unit for electrical field strength? So field strength is newtons per coulomb. A newton is a joule per meter over coulomb, which is this one, so A can be used, and a joule per meter amp second, so joules over amp seconds meters is 1, or newtons over amp seconds is 1. So that means that it's the final one that is not correct, which isn't one of those. A capacitor stores a charge of 600 microcoulombs when charged to a potential difference of 6 volts. What will be the potential difference across the plates if the charge stored increases by 50%? So Q, you have 1.5 Q, which means you have 1.5 V. So that's going to be 6 times 1.5, which is going to be 9 volts. The graph shows the results of an experiment carried out to investigate the relationship between Q and V across it, so very much similar to the last question. Which one of the following statements is not correct? Okay, so the energy stored can be calculated by finding the area under the line, so the area under would be half QV, which is correct. If the capacitor has a smaller capacitance, and we use the gradient, the graph would be steeper, so Q equals CV, so that means V is 1 over CQ. So a smaller capacitance would mean a larger 1 over C value, which would give you a steeper gradient. That's absolutely correct. If Q were doubled, the energy stored would be quadrupled. Yes, because energy is half Q squared over C, so that's true. Gradient of the graph is equal to capacitance. No, rubbish. We've just shown that it's not. A 10 microfarad capacitor is fully charged to a PD of 3000 volts. The energy stored can be used to lift a load of 5 through H. What is the value of H? So we need to work out the energy stored, which is half CV squared. So it's 0.5 times 10 times 10 to the minus 6 times 3000 squared, which is 45 joules. So we divide that by the mass. Divide that by 9.81, gives you a height of 0.9 meters there, which is that one. A horizontal straight wire of length 0.3 meters carries a current of 2 amps perpendicular to a horizontal uniform magnetic field of flux density this. The wire floats in equilibrium, which must mean the weight force essentially is equal to the magnetic force. So the force on it is BIL, which is 5 times 10 to the minus 2 times by 2 times by 0.3, 0.03, which must be equal to the weight force. So let's divide by 9.81 to get the mass, which would be 3.05 times 10 to the minus 3, so 3 times 3.1 times 10 to the minus 3. When a beta particle moves at right angles through a uniform magnetic field, it experiences a force F. An alpha particle moves at right angles through a magnetic field twice Mach flux density with velocity 1/10 the velocity. What is the magnitude of the force? So remember, force equals BQV. So what we've done is we've done double the flux density. We've got times 2 the charge because it's an alpha particle, but then we've done it at 1/10 the speed, so that's going to be 4 over 10, which is 0.4 F, which is B. Charged particles, each of mass m and charge q, travel at constant speed in a circle radius r. You've got a magnetic field, flux density B. What gives the frequency? So we know that 2 pi f squared r m is equal to BQV. So we can take the m over to the other side, and we can take the r over to the other side. So we end up with 2 pi f squared is BQ omega, and omega is 2 pi f. So we can cancel one of those. So we get the frequency would be BQ over 2 pi, oh, I've lost the m, so there'd be still an m in there. So it's going to be BQ over 2 pi m, which is answer A. $500-ton coil, cross-sectional area 4 times 10 to the minus 3. It's placed with its plane perpendicular to the magnetic field with a flux density 7.5 times 10 to the minus 4. What is the value of the flux linkage? So it's BA AN 7.5 times 10 to the minus 4 times 4 times 10 to the minus 3 times 500 gives you 1.5 times 10 to the minus 3 Weber turns. So we're just using BAN, which is B, so 23. Okay, output EMF of a simple AC generator can be increased by any of the four factors listed. Which one of these factors should not be changed if the frequency of the output is to remain unaffected when the EMF is increased? Okay, so we don't want to affect the frequency, so we know that omega is 2 pi f, so if we change the speed, we change the frequency, so it's going to be answer number C. Which one of the following would not reduce the energy losses in a transformer? Using thinner wire for the windings. Thinner wire would mean increased resistance, which would definitely not reduce energy, so it would be that one. Let's just check the others. Lamination reduces losses. Iron is a better magnetic material, so it's a softer magnetic material, so that's a good thing, so it improves your efficiency. And improve flux conduction again, so yes, it's going to be number A.